Choice of element for integration. The principal difficulty with the theory often lies not on its concepts but in the procedure for applying it. With mass centers and centroid, the concept of moment principle is simple enough. The difficult steps are to choice of the differential elements and setting up the integrals. The following 5 guidelines will be useful to choice of the differential element and setting integrals. The first is order of element. Whenever possible, a first-order differential element should be selected in preference to a higher-order element. Whenever possible, a first-order differential element should be selected in preference to a higher order element. So that only one integration will be required to cover the entire figure. Only one integration will be required to cover the entire figure. Consider this picture, a first order horizontal strip of the A. This picture provides an example. In this example, a first order horizontal strip of area dAL dy will require only one integration with respect to y to cover the entire figure. In the part 1, dA L dy, one integration. And L equals to the difference between these two functions, fx1, fx2, f2x, f1 the second order element dx dy will require two integration if we use this picture. dA dx dy, two integration. As further example for the solid cone in the picture here, we choose a first order element in the former circular slice of the volume. First order, we can write dA as an element, P R to dA. First order, one integration. And D is going to be dB. Also dV equals to three order. Three integration. Continuity is the second node to choosing element. Whenever possible, we choose an element which can be integrated in one continuous operation to cover the figure. We choose an element which can be integrated in one continuous operation. To cover the figure. Thus, the horizontal strip, for example, in the two previous provided picture, this picture, the horizontal strip would be preferable to the vertical strip in the picture here. In this picture, the horizontal is preferable to this vertical element, which if used we would require to separate integral because of the discontinuity in the expression of the height of the strip x equals to x1. The next note is discarding the higher order terms. Higher order terms may always be dropped compared with the lower order terms. Thus, the vertical strip of area under the curve in the picture shown in this figure. In this figure, we have this relation dA equals to y plus dy multiplied to dx y dx plus dy dx. We can drop it the higher order, and dA can be written as y dx. Approximately. The next note is choice of appropriate coordinate. As a general rule, we choose the coordinate system which best matches the boundaries of the figure. Thus, the boundaries of the area, for example, in this picture, in these pictures was easily described in rectangular coordinate, this part, and whereas the boundaries of the circular of the figure B in circular are best suited for polar coordinates. Next note is the centroid coordinate of elements. When a first or second order differential element is chosen, it is essential to use coordinate of the centroid of the element for the moment arm in expression the momentum of differential equation. The momentum of differential moment element. Thus, for horizontal strip of the area in the example here, thus for the horizontal strip of area in the picture A, the moment of dA above the y-axis is xcdA dm xc multiplied to dA, where xc is the x-coordinate of the centroid of C. X centroid element C dm. Note that xc is not the x which describe either boundary of area in the y direction. For this element, the moments of yc in the x direction and dmy and dm on the x direction in the y axis equals ycdA. In the limit as the y coordinate of two boundaries, yc centroid of element C. As a second example, consider the half cone of the picture here. We have also a, for example, dm z xc multiplied to the dA and dm x z c dA and dm y ycdA. Anyway, we have three components for x as a centroid of mass xcdA on A, ycdA on A, and zcdA on A. X, y, and zc, xc, yc, and zc are the centroid of selected element. With this example in mind, we rewrite the equation as this expression. It is essential to recognize that subscriptions C serve a reminder that the moment R appeared in the numerator of the integral expression. For moments are always the coordinate of centroid of the particular element. We can also write for the volume case, and for a general volume, this relation x equals to x dv on v, y c dv on v, and z c dv on v. All of c positions are the centroid of the selected element. At this point, you should be certain to understand clearly this principle of moments which was introduced. You should recognize the physical meaning of this particular as it's applied to the system of parallel weight force depicted in this picture. Keep in mind the equivalent between the moment of resultant weight and the sum of the moment of elemental weight dW to avoid mistaken setting of the necessary mathematics. Recognition of principle of moments will help in obtaining the correct expression for the moment of xc, yc, and zc of the centroid of the chosen differential element. Keeping in mind the physical picture of the principle of moments, we will recognize that all equations which are geometric relations are described also of homogeneous physical bodies because the density rho cancels. If the density of the body is in equation is not constant but varies throughout the body as some function of the coordinate, then it will not cancel from the numerator and denominator of the mass center expression. In this event, we should use appropriate equation. There are various examples related to center of mass or center of gravity for the various shapes in the sample problem solved in the related videos. The next section is about composite bodies and figures.